Hey, Nines, welcome to Thursday's session on Pythagoras theorem. We're going to take a look at exercise 3A now. So we're done with chapter 5, and the next part of measurement topic is Pythagoras. So I'm not sure if you've encountered this last year, but you should have. Now, who is Pythagoras is sort of the first thing we need to figure out. Pythagoras was a person, an ancient Greek philosopher who lived many thousands of years ago, between the years 570 BC and 495 BC. What he figured out was how to find the unknown side of right angle triangles when you know the length of two sides already. Now, before we get into the examples, let's see Pythagoras' proof. So with any right angle triangles, remember his proof only works for right angle triangles, not scalene, not isosceles, it has to be a right angle. His proof goes like this. A and B are your two shorter sides. Now, if we know the side length of A and B, what we can do is we can draw these little squares, and we can call this square the A square. Right, so if we were to just connect the solid lines, oh, not bad. Not bad. So imagine that's a perfect square, right? And we call that the A square. And if we know the B side length, then we can also draw out a B square. And why are we drawing these B squares and A squares, I will show you in a moment. The reason being is if we knew what number goes where the A is and where a number that goes where the B is, we can actually find the area of these squares. All right, if we call this the B square, all right, this is our B square. Let's try and make it a solid line. Not too bad. What Pythagoras figured out was, well, these two squares added together gets you this imaginary C square that's coming off the longest side length, right? So let's imagine we've got a square here as well. I think that's slightly crooked. I'm sure you get the gist. Oh. Right, so imagine there's like a perfect square here too. That's awful. Let's try that again. All right, that's slightly better. So this is the biggest square of them all, our C square. All right, so A square, B square, and C square. What he figured out was these two squares area, so the A squares area and the B squares area, added together gets you the C squares area. And when you know the area of a square, are you able to find the side length? Yeah, you can. Why? Because all squares have the same side length, correct? And so what you do is you would just square root the area inside to get your side length. For example, if we had A as the number 3, so let's scribble out this. If we had A as the number 3, what would this square be? If you said 3 squared, you are spot on. So what would the area of this square be? 3 square is 9. So 3 squared equals 9, right? What about B here? What if we scribbled out B and replace this with a 4? what would this b squared here become? Well, this would become 4 squared. Do you agree? So this square here would be 4 squared. And what's 4 squared? 4 squared would be 16. But because we don't know what the c square is, we know the area of c square is going to be these two squares added together. So what is 9 plus 16? If you said 25, you are spot on. Now, is 25 going to be the length of this line? Probably not, because you've got a let's say 3 centimeter line here, a 4 centimeter line down there. There's no way this line here is going to be 25, right? But if we square root the 25, what do we get? We get 5, don't we? Now, what do you notice? What's a 5 by 5 square going to be in area? If you said 25, you are spot on. Okay, so that's how he stumbled upon the right angle triangle theorem, or the Pythagoras theorem, named after himself, because he imagined there were squares branching off the two smaller sides, and if you added the two smaller squares' area together, you actually get the area of the larger square, and when you get the area of the larger square, you square root to get your length. All right, that might sound a little bit confusing for now, but what we're going to do now is just take a look at his theorem. So his theorem's formula is the c squared, or the c square. Let's go back and change this in blue. Is equal to the a squares area plus the b squares area. All right, so in plain simple English, this means the c squares area equals the a squares area plus the b squares area. Oops, this spot should be down here, shouldn't it? Plus the b squares area. And from there, we can actually figure out the length of the longest side. Let's do an example together. So, example 1 says, find the length of the hypotenuse. Here's one critical detail we didn't go through up top. The hypotenuse is always the longest side. All right, so this side length here, hypotenuse, is always the longest side. And what do we notice about the hypotenuse? It's always opposite the right angle, okay? And if we go back to our example here, the hypotenuse, the longest side, is on the diagonal, and it's always opposite the right angle. So hypotenuse on a diagonal slant and opposite the right angle always. So we write our formula, c square equals the a square plus the b square. Now, which side is A? Which side? We know which side is C. But which side is A and B? It doesn't really matter. But for your benefit, just go with the shorter side being A and the second shortest being B. So if we were to be consistent with our color coding above, all right, the A side is going to be the 5. So it's really important we show our working out here. So this is going to be 5 squared. It's a shame they didn't put a unit here because we'd just be in normal centimeters, meters, normal metric units. The B side here is going to be 12. And then the C squared is, well, C squared. And so what do we do now? Well, we can actually fix up. So we'll write our little therefore. We can fix up the right side, can't we? So we know we can add together 5 squared and 12 squared. So 5 squared is what? 25. 12 squared is 144. Using our BidMath rules, we couldn't add them together. We can't go 17 squared because we've got to get rid of the index first using BidMath. That's why it's 25 plus 144 instead of 17 squared. And so what is 25 plus 144? That gets us 169. Now, is this side length here going to be 169 when the two shorter sides are 5 and 12? No way. If this is 169, this line would go all the way down to the bottom of the page based on the ratio they're given here with the two shorter sides. So what do we figure out here? What's 169? If you answer with 169 is the area of this imaginary C squared, you are spot on. So if we know the area of the C square is 169, let's say centimeters squared, how do we figure out this length of the square? If you said we square root, you are spot on. So to get rid of this square root, what we do here is we say C equals square root. So notice how this square has been transferred into the square root. 169. And square root of 169 is going to be, if you punch it in your calculator or if you know your times table off the top of your head, it's going to be 13. Right, that's looking a lot more reasonable. 13 is a reasonable size, okay, for 5 and 12, respectively, on the shorter sides of the right angle triangle. Now, the hypotenuse is always going to be the largest or the longest length. So if your answer is below 12, well, then you're wrong. Okay, you're working out somewhere. Was incorrect. But that's a process for the first right angle triangle. Let's have a go at the second one. Right, here what we have is, it says for us to round to 2 decimal places in part B. So this is part B now. What we always have to do is write the formula. C squared equals A squared plus the B square. What is our C squared here? Oh, well, we don't know. And you know, sometimes they might call this X, and then you just replace it with X squared. That's fine. Doesn't matter what pronumeral, it could be A, B, C, D, E, all the way down to Z. Again, the A and B doesn't matter, but just for consistency's sake, we'll say the shorter side is A. So let's say this is 7 squared. Why doesn't it matter? Because if you were to sub 12 back here, it'll be 12 squared plus 5 squared, which is 144 plus 25, which doesn't make a difference. And that's really important later on. But yeah, just for now, know that it doesn't really matter which two short sides you sub into A and B. You can sub into 9.5 with the A, if you like. But anyway, let's just continue with the shorter sides being A. The B here would then have to be 9.5. Right, so if you subbed in 9.5 here, then this one would be 7. 7 squared. Right. From here, well, we know that 7 squared is 49. Using our laws of BIDMaths, we have to remove the index first before we can add. The 9.5 squared, let's see what that is. 5 squared equals 90.25. Add the two together. Keep in mind don't forget our c squared, so this always has to keep carrying down. And it's important you keep writing it because of this little arrow when you go in square root. Well, what this adds up to is 139.25. Right, so these two added together. And we know this side isn't 139.25 because if it was, the whole line would be off the page. So what did we figure out here? What's the 139.25 for? If you answered with, that's the area of the imaginary c square, or the c square, then you are correct. So if we drew out the square here, the area of this square is 139.25. Now, how do we find the side length? Again, to get rid of this little square symbol, or to find the side length of any square, you would have to square root. So we would have to square root 139.25. Right, what is the square root of 139.25? Let's see. $11.8. So therefore, our C side is going to be 11.8 or 80. Okay, because it says round to 2, but 11.8 is fine. Just remember, if the question has centimeters, meters to include the units, unfortunately we don't have any here for some reason. They've just left it as numbers and no units. But yeah, that's sort of how you figure out the hypotenuse, which is the longer side. Just one quick technical thing. This is actually what we call the exact answer. So this here with a square root is exact answer. This here is what we call the rounded answer. All right, here's rounded. And here is the exact. Why? Because in the next section it says, find the length of the hypotenuse in this right angled triangle, leaving your answers as an exact value. It's literally the same process, but instead of going past the square root sign, okay, we just leave it like so. We don't need to go into the decimals. That's all it is. It's just a minor technicality. So let's write out our formula and figure out what the hypotenuse is. So the hypotenuse here we're trying to figure out is the c. So we have c squared equals a squared. Mixed the colors up. C squared equals a squared plus b squared. So we know c squared is what we're trying to figure out because c squared is always the hypotenuse, the longer side. The a square, well, is always the shortest, but again, it doesn't matter if you want to sub in 5 or 2. So let's, for consistency's sake, we'll sub in the 2. That's 2 squared. Our b squared is going to be the other known side, right? So from there, we can say c squared is going to be whatever 2 square is, which is 4, because 2 times 2 is 4. Whatever 5 squared is, again, if you're not sure, just use a calculator. 5 times 5 gets us 25. We can add the 2 together. What's 5 plus? No, sorry, what's 4 plus 25? 29. And so this therefore means C, remember how we then have to square root the other side, because this is the area of the C squared. To find the length of the square, we have to square root 29. And this is our exact answer. And we no longer need to go any further. Right, let's jump to exercise 3A and take a look at questions 4, 5, 6, and 7. All right, in the old textbook, that's questions 1, 2, 3, and 4 in the new textbook. All right, that's all, everyone. Thanks.